Hello everyone. In this session, we are discussing the acidic character of carboxylic acids, and then we'll move on to compare the acidic strength of carboxylic acids with that of alcohols and phenols. So, carboxylic acids exhibit resonance. These are the two resonating structures of acids, and in one of them, we can see that oxygen has developed a positive charge, and because of which this bond pair shifts towards oxygen. As soon as there is shifting of a bond pair towards one entity, the bond is weakened, and weakening of this OH bond leads to release of H plus and indicates acidic strength. But the acidic character of a RCOOH or carboxylic acids would be incomplete without justifying the stability of the carboxylate anion. So the carboxylate anion also exhibits resonance. What we need to show here is that if we want to show the RCOOH molecule being an acid, the availability of H plus should be there, and H plus will be available if RCOO minus ion will be stable. So we need to show that this anion is more stable than this undissociated molecule. So we are going to try to justify greater resonance stabilization of the carboxylate anion as compared to the resonance stabilization of the undissociated acid molecule. And how do we do that? Point 1, that the resonating structures of the anion are equivalent resonating structures. And what's that? Equivalent means they are similar resonating structures. O with 6 electrons minus, 6 electrons minus, and the other oxygen with a double bond and a double bond. And because of equivalent resonating structures, the negative charge is not localized over only one oxygen but is dispersed equally over two oxygen atoms, and because of which what's going to happen, that this H plus will not have one center only to hit. It is sort of confused whether to hit this oxygen or this oxygen. Therefore, because the negative charge is not localized over one oxygen but is dispersed equally over two oxygens, this imparts greater stability to the resonating structures of the carboxylate anion. And the second is that in the resonating structures of the anion there is no charge separation, unlike the presence of two opposite charges in the undissociated molecule. And as soon as there is charge separation or two charges, the molecule becomes or comes to a higher energy level, and a higher energy level implies lower stability. And so absence of charge separation in the carboxylate anion brings it to a relatively lower energy level and therefore greater stabilization. As a result, the equilibrium will shift in this direction, making the carboxylate anion more stable than the undissociated molecule. If this is stable, that means H plus is available in this solution, and we can justify the acidic character of carboxylic acids. Now let us see how we could compare the acidic strengths of different entities on or different acids on the basis of Ka or pKa values. What is Ka? Dissociation constant for the acid. So I have here acid in aqueous medium giving carboxylate anion in aqueous medium AQ and hydronium ion. Using the law of mass action and law of chemical equilibrium, we know what is equilibrium constant or dissociation constant in this case, product concentrations upon reactant concentrations. Since the aqueous medium is taken in a large excess, its concentration either is taken as 1 or is taken as constant. So this constant multiplied with this constant value becomes a new constant Ka, which is known as the dissociation constant for the acid, and happens to be constant for a given acid depending on the temperature at which it is being read. So Ka becomes equal to the carboxylate anion into the hydrogen or hydronium ion upon the undissociated molecule. So how do we compare acidic strengths on the basis of Ka? So from this expression, we know that we already know that an acid is a good acid if it provides a large number of H pluses or hydronium ions in solution. And from this expression we can see Ka and hydronium ions are directly proportional. So, acid strength is proportional to hydronium ion concentration. Ka mathematically is proportional to hydronium ion. Therefore, acid strength is also directly proportional to Ka, which implies greater the value of Ka, greater is the acid strength of that example under context, and lower is the pKa value. Why? Because pKa is the negative logarithm of Ka. Now, in a very, very important study, that is comparative study of the acidic strength of alcohols, phenols, and carboxylic acids. So, do remember that the strength of the acid is as much as the stability of the conjugate base. What is the conjugate base? After the acidic entity has released a proton, the negatively charged anion that is formed is our conjugate base. Greater the stability of the conjugate base, greater is the acidic strength. So over here we are going to try to justify or try to show which conjugate base is the most stable, and whichever is most stable would be the most acidic. So we have alcohol in aqueous medium giving alkoxide ion and hydronium ion. Alkoxide ion is the least stable of the three. Why? Point 1, it is not showing resonance, so there is no contribution to stabilization via resonance. And second point is that the R ion is showing plus I effect. What is plus I effect? Electron releasing effect. And because of that, the R group shifts electrons towards the oxygen, which becomes more electron rich and more susceptible to attack by this positive proton, leading the equilibrium to this direction. So this happens to be more stable as compared to the alkoxide ion, lowering acidic strength of the alcoholic entity. Let's talk of phenol now. Phenol in aqueous medium produces hydronium or H plus ion and the conjugate base phenoxide ion. Phenoxide ion is more stable than the alkoxide ion since it is exhibiting resonance stabilization. So this comparison is complete. But now let us talk about the comparative stability of the conjugate bases of the phenoxide and the carboxylate anion. In the case of phenoxide ion, the negative charge is present only over one oxygen atom. And in some resonating structures, you may refer to the previous session, in some resonating structures of the phenoxide ion, the negative charge, of course, is delocalized over the ring, but it is over the more electronegative, over the less electronegative carbon atom, which contributes to lesser resonance stabilization. I'll repeat that. As compared to alkoxide, more stable because it is showing resonance. This didn't show resonance. But in comparison to the carboxylate anion, here the negative charge is only localized over one oxygen atom. Also, in some resonating structures of the phenoxide ion, the negative charge is moving on the ring over the less electronegative carbon atom, which contributes to a lesser extent with respect to resonance stabilization. However, if we talk of RCOOH giving us the conjugate base RCOO minus, which is the carboxylate anion, this happens to be the most stable conjugate base. Which one? RCOO minus. Why? Because it has equivalent resonating structures. Therefore, the negative charge is equally dispersed over two oxygen atoms, which contributes to greater stabilization. And also, the negative charge is present over the more electronegative oxygen atom in this case, as compared to this place where in some structures it was over one oxygen and in some structures it was delocalized over the ring on the less electronegative carbon atom. So because of equivalent resonating structures, because of the negative charge being dispersed over two oxygen atoms, and also the negative charge being available on the more electronegative atom, that is oxygen, the carboxylate anion is more resonance stabilized as compared to the phenoxide ion, and therefore out of the three this is the most acidic. So if we were to compare the acidic strength here, alcohols would be less acidic than phenol, which would be less acidic than carboxylic acid. Do remember to repeat, revise, and reinforce, because only a repeated study will fetch you great scores and success. Till then, good luck, all the best. And in the next session, we'll be doing effects of substituents on the acid strength of carboxylic acids.